All right, so today's notes are on function operations and composite functions, and our content objective is to add, subtract, multiply, and divide functions and find their composites. Our language objective is to use the correct terminology, including sum, difference, product, quotient, and composite to explain function operations. So first thing I wanted to quickly review is function notation. So we talked about this earlier this year, I believe in Unit 1, but in case you've forgotten, function notation is this right here. So this is function notation. It's read as f of x. So f of x, what's in the parentheses is what's being substituted for x. If there's nothing being substituted, it's just left as x. And then the f of x, that whole part, is the whole function. So f of x represents the whole function, or the y value, or the output. So these are, f of x can represent any of those things. So the whole function itself, the y value, or the output of the function. But it's read as f of x, and what's in here is what is being substituted for x. So I just made up a random function for the right side of the equation. The important thing I want you to remember is what these components represent. So that's what is substituted or inputted. The whole thing is the output, or the whole function, or the y value. And it's read as f of x. This, right, I gave you the most common example, f of x. You might also see g of x or h of x. It doesn't, the letter tells you or differentiates between different functions. So we'll be working with multiple functions in this section. So you'll see f of x, g of x, h of x, and lots of other functions. The letter that's in front just names the function or tells you, refers to a specific function itself. All right, so moving on, the operations we're going to be focusing on today are addition, subtraction, multiplication, and division, and then composite. So we're going to start with these because they're a little bit more straightforward, and then we'll jump into composite for the second part. So when you're adding functions, all you're doing is taking each function separately and then adding them, combining like terms. Subtracting, same thing, you take one and subtract the other, you just put parentheses around the whole second function, distribute, combine like terms. Multiplication, you'd have to multiply them, so that might entail foiling or distributing, but you just take each function and multiply them together, and that will give you your answer. Division, same thing, you just take each function. So if this were x plus 1 and this were x, then you'd just do x plus 1 over x. It's pretty straightforward. So I'll do a couple examples of that, especially when we get into domain, but I think you'll find that these are not too crazy, or they're things you're used to doing with manipulating algebraically. Composite functions are a little bit different. So one thing I want to note is multiplication. Notice that it's a closed circle when you're multiplying, so it's a closed dot when you're multiplying. Composite functions use an open dot to represent composites, and this just means that you're plugging one function into another. I'll spend more time on that later, so I'm not going to delve into it now, but the key thing I want to differentiate between is closed circle multiplication, open circle composite. Closed multiplication, open composite. That's going to be important, so you're performing the correct operation as you do this. The next thing I want to talk about is the domain, which, as you hopefully remember, is the x values, the input of a function. So when you're doing these operations, the domain is going to be the x values and the domains of both of the functions. So when you do addition, subtraction, multiplication, division, or find the sum, difference, product, or quotient, the domain is going to be whatever values make both functions work. So it has to be the domain of, or within the domain of both functions in order to be in the domain of the function operation. I'll show you what that means. Quotient, in addition to that, also you need to make sure that it doesn't, you don't have anything that would make the original denominator equal to 0. So as you may remember, you're never allowed to divide by 0. So that's still true here. You can't have a denominator that would be equal to 0. The only thing you have to remember is it's the original denominator, not the denominator once you've simplified. So that's a lot of theoretical information. Let's jump into some examples. So I'm going to flip the page for an example. So the first thing I want to try as a quick check. So if you understood what I was getting at there, I'd love you to try this on your own. But I'm going to go over it for the sake of time. So pause it, try it on your own. I'm going to go over it. So f plus g, so I have f of x equals 4x plus 7, g of x equals square root of x plus x, and I'm finding f plus g, or f plus g of x. You could write it this way or this way. Both are acceptable, or f of x plus g of x, all acceptable ways to write this. What this means is I take 4x plus 7 and I add square root of x plus x, and that would be my new function. The only thing is I want to simplify and combine like terms. So I can combine 4x with x and I get 5x plus 7 plus square root of x, which traditionally you want to write the x's before the constant by descending order of degree. Since this would be 1/2, this would be my function. So my new function f plus g of x would be 5x plus square root of x plus 7. And that's my answer. The only other piece I want to talk about is the domain. So if I look at the domain, here, this is a linear function. I could plug in anything and I'm not going to ever get undefined. So I could plug in any number, it'll never be undefined. So that domain is all real numbers. This domain, so f of x, the domain would be all reals. G of x, the domain would be, since I have a square root, I know I'm not allowed to have a negative square root. So my domain for g of x would have to be x is greater than or equal to 0. So my domain, since this is all reals, this is more restrictive, I have to go with the more restrictive domain and say that the domain would be x is greater than or equal to 0, because I don't ever want to plug in a negative number and get an undefined value under my square root. So I have to say x is greater than or equal to 0. So this is going to be similar. The only thing is now I need to remember to put parentheses around my second equation because I need to distribute this negative. So I distribute that negative to both components when I'm subtracting them, and I get this. I combine my like terms, so this time I have 3x minus square root of x plus 7, and that will be my final, sorry, that's a minus g of x. F minus g of x equals 3x minus square root of x plus 7. And again, if I look at my domain from these, my domain will be x is greater than or equal to 0, since that is the more restrictive domain. All right, so the next thing I'm going to do is another example. So I want you guys to try another one to see multiplication and division. So quick check, I want us to let f of x equal x squared minus 9 and g of x to equal x plus 3. And I want us to find f times g and f divided by g. So I want you to find both of those and determine their domains, but we'll talk about that after. So try it on your own. I'm going to go over it now. So f times g, I have x squared minus 9 times x plus 3. I'm just going to multiply each of these functions. So I'm just doing this whole function times this whole function. I FOIL it and I get x cubed plus 3x squared minus 9x minus 27. So I just FOILed that out. And then I can't combine any like terms, so this is going to be my final function, f times g of x, and that is that. So then I'm going to look at my domain. And here again, my f of x, it's a quadratic. I can plug in any value in there and it will be fine. So it's all real numbers. G of x this time, if I look at it, there's no square roots, there's no variables in the denominator, so I'm going to also have all real numbers. So my domain for my product will be all real numbers. So the next one gets a little bit trickier. So again, I'm doing x squared minus 9, but this time it's going to be divided by x plus 3. So for this one, you actually do have to do a little more work in simplifying. So hopefully you recognize what this is. If you don't, please pay attention, write this down, put a star reminder to yourself. I have x squared minus 9. That's the difference of squares. So it's going to factor to x plus 3, x minus 3, all over x plus 3. And because this is all factored out, I can cancel my denominator and the x plus 3 in the numerator and the denominator, and I'm left with just f over g of x equals x minus 3. So that would be my entire function. The only thing I need to clarify is my domain. And this, as we saw in the last one, would be all real numbers for both these components. But what's tricky here is we also have to account for having a variable in the denominator. So since our original function had x plus 3 in the denominator, I need to account for that and say x plus 3 can't be 0. So my original denominator can't be 0, which means that x cannot be negative 3. So my domain here will be x does not equal negative 3. So my domain is a little bit narrower. X cannot be negative 3. Okay, so that's all for function operations for now. We will definitely have some time to practice that in class, but I want to do composite functions as our last and final thing for today. So I'm going to flip over this page and talk about composite functions. So this is our last page. So a composite function is when the output of one function becomes the input for another. So I plug something into F, so I input something to F, I get an output. Then you're going to take that output and make it the input of G, and then plug it in to G and get your final answer. So a composite function is when you plug something in, basically double plug it in. So plug it in once to a function, then plug it into another function when you get out an answer. It's important to note that the order matters. So plugging f of g of x is not the same as g of f of x. So when you plug something into f, get an answer, then plug it into g, that doesn't necessarily mean that when you plug something into g and then into f, you'll get the same answer. So let's go over how this would look with an actual example. So let f of x equal x minus 5, g of x equal x squared. I want us to find g of f of negative 3. So again, notice that that little dot is also read as of. So it's g of f of negative 3. So all we have to do to solve this is substitute from the inside out. So I'm going to plug negative 3 into f. So f of negative 3 is equal to negative 3 minus 5, which is negative 8. So I get negative 8 here, so I'm writing some steps off to the side. Then I'm going to take the negative 8 and plug it into g. So I take g, so I got my answer, now I'm plugging it into g. So you plug in negative 3 to f, get an answer, plug it into g. So I have g of negative 8 is equal to negative 8 squared. Negative 8 squared is 64. So my answer is going to be g of f of negative 3 is equal to 64. And that's all you have to do. Some of these will get into more complicated values when we don't plug in a number. We're actually plugging in whole functions, but for now I want us to focus on just the numbers. So pause this, try these last quick checks. I'm going to go over them. So this is the same thing, plugging from the inside out. So g of negative 3 is going to be negative 3 squared, which is 9. Then I take the 9 and plug it into f. So I have f of 9 is equal to 9 minus 5, which would be 4. So I can say f of g of negative 3 is equal to 4. And my last example, final thing, I'm plugging in 2 into f. So I have f of 2 is equal to 2 minus 5, which is negative 3. And then I'm plugging that into g. So I have g of negative 3 is equal to negative 3 squared, which is 9. So I can say that g of f of 2 is equal to 9. So that's all for today. Make sure you write down questions, comments, or concerns so we can go over them together in class.